Welcome back to Pollys Introduction to Computer Networks. Now let's check out the assignments during this Saturday. First of all, there's one PA number 5 will be doing this Saturday, and 4 quizzes to complete as well this week. Among the 4, just quiz 19 being a little bit tricky. It's an open-ended quiz. The other 3s are, however, straightforward. And by the way, many of you are probably waiting for the exam 1 results. The results will be out tomorrow at about 1 p.m. right after the lectures. All right, so the topics today. RDT 2.1 is going to be the first one, and just a little bit of review from last week. We're in the transport layer chapter. One of the major functioning the transport layer. Hi, Isa. Okay, hi, by the way. One of the major functioning the transport layer is reliable data transfer. That's what RDT stands for. And we introduced, feel free to pop up and say hi. As Polly trying to review what we've talked about last week. So RDT 1.0, if you recall, it's trivial because we assume the underlying channel is reliable. So, hey, reliable data transfer was not an issue in that case. Therefore, you see the finite state machine works in a very trivial way. Sender simply sends, receiver simply receives. And hey, that is, just not the real world. Okay, so to make it a little bit more realistic, we relax the assumption about the underlying channel. In RDT 2.0, we allow bit errors, recall. But we allow bit errors from the sender to the receiver, so only the data direction. Okay. And the solution is straightforward, if you recall. What we do is to add a checksum to the packet before the sender sends it out. At the receiver end, receivers does the checksum test. If it passes, that means no bit error, the packet is not corrupted, therefore we send back a positive acknowledgement. Now in case the checksum test fail, then there's a bit error somewhere. Packet is corrupted. The receiver sends back a negative acknowledgement. And that is RDT 2.0. Now, RDT 2.1 is simply saying that, hey, what about the other direction? The AX and NAX, they could also suffer from bit errors. So RDT 2.1 is to handle the error from the other direction. So this first video we'll be playing, only 2 minutes. It's actually just to review RDT 2.1. Now, this slide is called discussion, but what it does is really the summary of 2.1. So at the sender side, what's being special is this. Sender checks whether the ACNAC is corrupted. Now, in order to prevent having duplicate packets, the sender side now also assign a sequence number to the data packet sent. So it's either 0 or 1. And in order to track data packets carrying the sequence number, there are now twice the amount of states and twice the amount of the transitions. So the state somehow need to remember what is the expected sequence number. Receiver side, the primary function is to avoid receiving duplicate packets. So it would check the sequence number, whether it's a repeating sequence number. In that case, the packet is a duplicate. If that is the case, the data will not be extracted, passed up to the application. It's just going to be discarded. But be careful. Receiver here seeing a duplicate, although not extracting data, not passing it up to the application, it will still what? Send an ACK out again. All right. Why? Because the former ACK or NAC being sent back to the sender. Only the sender knows whether the packet is corrupted. And if it's corrupted, the sender doesn't even know whether it's an ACK or NAC. So sender there is trying to be fuzzy and do the best thing that he can do, which is to repeat sending the data that has been previously sent. So receiver here needs to be more considerate. In case it's a duplicate packet, send back the ACK again, just in case it's an ACK packet being sent back and it's corrupted at the sender. Now at least the sender will be informed. Everything is okay and move on. All right, so let's move on to RDT 2.2 as well. By the way, RDT 2.2 works just like 2.1. The only difference is the way we send the AG and NAGs. Okay, in 2.1, we set it in two different packets. But in 2.2, we'll just change that so that we send just an AG packet, but with a bit there indicating whether it's a positive or negative AG. This way, we will simplify the finite state machine significantly. Okay, so this video introduces RDT 2.2 about 3 minutes. RDT 2.2, it's essentially the same as 2.1 except here. It's going to be the NAG-free version of 2.1. By saying that, what I meant is, well, in 2.1, when the packet arrives at the receiver, okay, we send positive acknowledgement, that is ACK. Well, in case that data packet is corrupted, we send a negative acknowledgement, that is NAK. Now, as a result, we do have like two packet formats, right? One says I am acknowledgement, the other says I'm negative acknowledgement. So RDT 2.2 here is essentially to say, let's not have two different packet formats, just have one acknowledgement packet, but adds a bit in the acknowledgement packet, and we change the bit, okay, the value in the bit, to indicate whether it's really a positive acknowledgement or a negative acknowledgement. All right. So same functionality as 2.1, but using only AG packet. But the AG packet will be carrying an extra bit that is also the sequence number. Okay, so that is the sequence number bit. Okay, and the value in the sequence number bit is going to tell the sender whether this is a positive acknowledgement or a negative acknowledgement. All right. So now we have, a NAG-free protocol. Receiver sends acknowledgement packet for the last packet received. Okay. Think a little bit about it. So the receiver starting from waiting for call from below 0. Right? So if packet 0 is received okay, receiver here sends acknowledgement for packet 0. Because packet 0 received okay. The last packet received okay is what? Sequence number equals 0. Now, go to wait for call from below, packet 1. So if packet 1 arrives at the receiver and it's corrupted, what does receiver do? Which packet is the last received being okay? Well, 1 is not okay. So, still sending AG packet, but sequence number bit there is 0 again. All right. But at the sender side, what's going to happen is sender will receive the first AG with sequence number 0, right? Indicating packet 0 is received okay. But sender there is going to receive another sequence number 0 AG. Ooh. Hey, how come I get acknowledgement for sequence number 0 twice? Yeah, having duplicate acknowledgement at a particular sequence number that indicates the next data packet that sender just sent out was corrupted. A negative acknowledgement in a way. So receiving duplicate is essentially signaling, sender is sending a NAG, right? So sender there will have to what? Retransmit the packet that's last sent. So essentially, when the sender receiving an AG with a sequence number that's not expected, that's a NAG. Therefore, retransmit the packet. All right, so next video, I'm going to introduce the finite state machine of the receiver of RDT 2.2. And this time, instead of just, showing the finite state machine and then start explaining what the transitions meant, what Polly will be doing is to derive the receiver finite state machine of 2.2 from 2.1's receiver. Okay, then you see a little bit how one can come up with the finite state machine. Okay, but hey, with the derivation, so this video is a bit long, 5.5 minutes. Now let's try to develop RDT 2.2's finite state machines. So here what we will do is to borrow from 2.1 and start from the receiver side of the finite state machine. All right, so initial state is wait for 0 from below. So we're expecting data of 0, and we get 1. If it's not corrupted and indeed carrying sequence number 0, then we extract data, pass it up to the application layer, generate an AG packet with a checksum, and then send it out. Now, if it's 2.2, we'll be generating an ACK packet, all right, but this ACK packet should be carrying a sequence number, isn't it? And according to 2.2, the sequence number should be the last data packet received OK. Now, what is the sequence number of the data packet received OK? Well, we just actually what? Received 0. So, yep, you're correct. The ACK packet we're generating here for RDT 2.2 should carry sequence number 0. And so once we finish all the actions, we'll be finishing the transition and move to the next state, wait for 1 from below. And if we get packet 1 coming in, passing these conditions, so indeed carrying sequence number 1 in this data packet, then similarly, we take the data out, generate ACK, and send it out. And here, the ACK sequence number will be what? Data 1, the sequence number that we just received. So as a result, we could actually conclude the receiver side of RDT 2.2 should look more like this. And I'm ignoring the upper right part of the receiver's finite machine. So receiving a packet, not corrupted, carrying sequence number 1. The ACK packet will be generating, of course, it needs to be an ACK packet format, carrying checksum. It also carries what? The sequence number of the data we just received, OK, and which is 1 here. So for this other transition at the top, then it will be make packet 0 ACK checksum. Now, hey, the receiver side of RDT 2.1 actually have all these other transitions, right? So we only handle this part and extend it to 2.2. We will still have to extend these transitions so that it will work for 2.2. Now, these are actually exact mirror of each other, so let's just focus on one side. Okay. Now, let's pick this transition first and see if we could evolve it as well into 2.2. So this is receiving a data packet, but it's corrupted. So in 2.1, we send a negative acknowledgement. But for 2.2, we don't send negative acknowledgement packets anymore because we don't have that format. Instead, we send ACK. But we have to carry a specific sequence number to indicate whether this is really a positive acknowledgement or a negative acknowledgement. So, the rule of thumb generating the sequence number there is what? Who is the last data packet received OK? Now, receiver is currently waiting for data 0 coming from below. So what that means is that the last packet received OK should be carrying sequence number 1. So ACK here should give the sequence number of the data packet last received OK. So yep, it should be ACK1 here that we're sending back to the data center. Now, what about this other transition? Receiving a packet, not corrupted, but carrying sequence number 1. This is not the data 0 we're expecting. All right. How can this be happening? So this is the very odd situation where the previous data, ACK, being sent back to the sender gets corrupted, if you recall. ACK packet or negative acknowledgements can be corrupted now, right, in version 2. Now, if negative acknowledgement is corrupted, sender simply retransmit, no problem. But if positive acknowledgement gets corrupted, sender also retransmit. And that is this odd situation here. You already sent back an acknowledgement for data 1, and yet it's receiving data 1 again. Yep. So this is the situation. ACK packet gets corrupted, and so you're receiving a duplicate of data 1. So we do not extract data and pass it up to the application because that's going to repeat words, repeat letters, repeat sentences. Okay. So we only send back ACK. And this ACK should be what? Acting the last packet received OK, therefore also carrying sequence number 1. Okay. Now, if you look at this guy and this guy, both transitions, the actions they'll be taking will be identical now, right? Both sending acknowledgement packets carrying sequence number 1. So then perhaps we could just combine the two transitions. Receive a packet from below, checking if it's corrupted, or carrying sequence number 1, send ACK packet 1. Right? And you know what? ACK packet sequence number 1 is already being generated here. Send PKT, if you do not replace this variable's value, it will remain the same. And so if we just simply call this, then we just combine the two transitions and make it very brief, like this. RDT, either corrupt or carrying sequence number 1, simply send back the send packet that has been generated here, which is an ACK with sequence number 1. There, you see, IDT2.2's receiver is a lot simpler. Now, sender side, is there any change? Not much, I have to say. But it's straightforward. Now you have derived the receiver of 2.2. So this video quite short, 2.5 minutes. Now let's try to develop the sender's finite state machine. Again, let's borrow 2.1's sender finite state machine and start from there. This is the initial state. We wait for call from above. And if there is 1, then we generate starting from packet 0. And then we enter that wait for ACK state. Now, in case a NAC is in, we do have this is NAC check, isn't it? Okay. So if that is the case, we retransmit the data. Otherwise, everything is fine, and this is a positive ACK, so we do nothing and move to the next state and gets a call again from above. But the thing in 2.2 is this. Well, there's no such thing as negative acknowledgement packet. In fact, both negative acknowledgements are just ACK and carrying different sequence numbers. So this will also be a is ACK check, okay? But the difference is going to be the sequence number they are expecting being different. So what should be the sequence number we expect here to pass so that we move on to the next state? We are expecting 0, right? So the sequence number here should be carrying 0. So we should be checking is ACK and particularly sequence number being 0. Therefore, we can move on. Send the next packet. If everything goes well, we should be getting another ACK packet, then carrying sequence number what? 1, because we just sent out packet 1, right? Now, the NAC here, check can no longer be valid and will be also doing the is ACK check. But what should be the matching sequence number here to trigger this action? Well, we just send packet 0. If packet 0 was corrupted, the receiver would be what? Sending the last data packet received OK. So that should be what? Sequence number 1. Similarly, for the check here, it should also be is ACK, but sequence number what? 0. And that takes us to the sender side of the finite state machine. So we change this line as well as this line. So this line is what? Expecting 0, so check whether the sequence number equals 0. This is also now is ACK, and this should be carrying sequence number 1. All right, so IDT 2.2 sender isn't particularly more compact, okay, as opposed to the receiver. But that is fine. And that's the end of version 2. Now, to start version 3, we'll do it through quiz 19. Okay, and this is the interesting quiz this week, in fact. Okay, so quiz 19, and you can probably see, JJ Tokens has inspired Polly for the quiz. Okay, so the name of the quiz is The Lord of the Ring. It's a very famous novel, and you can see from the map on the right here. Yeah, this is the Middle Earth. It's the fantasy world in the novel. Okay, and so you're asked to situate yourself in the Battle of the Helm's Deep. Okay, so where's the Helm's Deep? Yeah, it's somewhere in the middle, okay, of the Middle Earth. Okay, and you know what? The evil wizard. Okay, the evil wizard Saruman. Saruman's troops are pushing into the Helm's Deep. And this Helm's Deep is a place where the tall horseman people live. Okay, and they call themselves the people of Rohan. Okay, and the king, okay, has no choice but to send a messenger to call for help from Gondor. And Gondor is here, further south. Okay, so King sends messengers through the White Mountains to Gondor to call for help. Okay, now the thing is this, the White Mountains, okay, it's a mountainous area. Okay, so no surprise, there are lots of these orcs that are loitering around and looking for food, okay, which includes a human, the passengers. Okay, so these passengers might not be able to get through the White Mountains. So you are asked to role play again, but this time as Gandalf the whys. Okay. How do you make sure that gong door gets the call for help? Okay. That is quiz 19. Let's move to the score. Okay, let me post the quiz PNG there. This is channel W8 quiz 19. All right. You guys have 6 minutes, and this is probably the quiz that you want to gather your teammates and have a discussion, because those who have unique solutions or creative solvers will get the bonus this time. Okay, let's start counting time. 6 minutes, guys. Yeah, this is an open-ended question, so feel free. This is a fantasy world anyway. Okay. Hey, by the way, you are asked to roleplay Gandalf. Gandalf is a very powerful wizard. Yeah, so we have a random drop by student here. ep13 says, estimate the time it takes for the passengers to go to Gondor and back, right? Because that way, the king of Rome will know that, there's probably something happened to the passenger. So send another one. So that was actually very complementary to Team 5's solution here, right? Yeah, Gondor, ask Gondor to send back an egg or fire or something like that. Okay, and if we don't see that egg, Rohan people will send another messenger to recover from the lost messenger. In the meantime, right? We wish the messenger rest in peace. Okay. I understand that the quiz is a little bit cruel, but hey, packet losses on the internet, very common despite being cruel. Okay. Let's see Team 2. First, we think that sending a giant eagle, exactly, okay, to carry the message. That would avoid the orcs entirely. Cool, because orcs don't fly. There you go. So it's called the out-of-band communication, right? You send important data out of the regular channel. Jeremy, cool idea. We gotta ask Gondor to mark his answer with, yeah, like a seal. You see, here's a little bit of, authentication mechanism that Jeremy is designing. Yeah, because otherwise, how do you know, right? The acknowledgement is coming back from Gondor. Then the king of Rohan will be mistaken, thinking that there's going to be help, but no, maybe the orc is the one sending the egg. Yeah, and Jeremy, you are perfectly right. And this is not why nowadays we send web objects through HTTPS instead of just HTTP. By the way, HTTPS runs on top of TLS, the secure version of TCP. Exactly, August. There you go. Now, all these mechanisms you've heard about can connect. And you can be Gandalf the Wise, devising mechanisms to rescue the Rohan people, right? Anthony here, just go around the mountains. How about that? Yeah. So if this particular path through the White Mountains is busy or, very dangerous to the packets or to the messengers, let's walk around, take another route. Maybe equal due to not having, good point, Anthony, right? If we go around the mountains, right, and going uphill is hard. So going around the mountains, the delay might be the same. Who knows, right? It makes a lot of sense. Send soldiers across the mountain periodically if one arrives. I see, interesting. So you kind of send these messengers multiple times. And periodically, and hopefully one of them at least arrived to Gondor, and Gondor somehow maybe lit a flame or lit a fire or generate smokes far enough or high enough so that the Rohan people can see. The ring is evil. Okay, we can use the power. I see. We have to send more men. Okay. Yeah, so I guess Team 6, Jingtao here, is proposing something a little bit similar to what Anthony was suggesting, right? You send multiple and periodically spread them out so that they don't get captured by orcs all at once. Right? And this is called the forward error correction. This is the other way of doing error recovery on the internet or for any communication network. Sending messenger, getting an egg, and resend. That is called the. I actually forgot. Okay, it's definitely not forward error correction. It's waiting for feedback and then correct. This is forward error correction, meaning that you anticipate errors and you send redundant data, and hopefully one of the redundant data arrive at the receiver. But you can see this approach here, team 6 and 1, yeah, bandwidth consumption is going to be higher. So it's likely a trade-off, but delay is going to be shorter, right? You don't have to wait for the approximated time for the messengers to go and back before resending. Let's see, team 4, we can send many messages, exactly, send 200 messages at least. Yeah. Yeah, that we can assume some confidence that the king of Gondor received the message. Yes. And it's probably a scale, right? It's not a binary issue. You can probably adjust the number of messages you send to enhance, okay, your security of receiving help from Gondor. Okay, this is from Justin. Nick, let me see. Assuming Gondor has a crystal ball. Hey, this is again out of band communication, right? Instead of sending messages physically, yeah, you do magic. Hey, this is 21st century, guys. Okay, what we did on internet is magic for people back in the 19th and 20th century or early 20th century. So all those things that you think magical now, it might just happen in the future. So I don't think that I don't think it's naive to think magical solutions. Tao said multiple waves of fast messengers. Yeah, sacrifice some. Oh, sorry about those. Necessary to save. Yeah, sometimes, isn't it? Yeah, when Polly was young, I thought life was about, receiving rewards, and being complimented. But as I grow older, I feel that life is more about sacrificing. That is exactly what you guys as parents did for you guys. And you guys eventually will also be parents. Well, okay, most of you will become parents, okay? And when you are one of those, you will see. Isa, she sent a magical butterfly. Oh, yeah, I thought butterfly is probably as secure as eagles, right? I think someone earlier mentioned sending eagles. Majestic, and they fly through the mountains. Butterflies also fly, and they are harmless, right? People wouldn't thought that they are the spies, okay, going from Helm's Deep to Gondor. Cool. Gandalf as an eagle friend, yeah. Hey, guys seem to like the eagle trick, and the ladies prefer the butterfly trick. Miguel, let's see. Miguel, you are a genius, okay? Sure, disguise as orcs, and then you can roam around without being discovered as a messenger. Cool. But before you arrive at Gondor, take off your disguise. Okay. But I cannot think of a way of implementing this on the internet. Guys, okay? Listen to Miguel, Team 3. Is there an equivalent of this on the internet? This would be really cool. Right? So if you can disguise the message as harmless, right, then the hackers wouldn't know, right? You encrypt some data, but they don't look like they're encrypted. GFW. Interesting. Cool. Yeah, so hey, how about tricking the hackers? Tricking the orcs. Yeah. So, hey guys, be creative also, trying to make your data secure. All right, so hey, quiz 19. It's in fact just to set stage for RDT 3.0. Okay, in the first video you will hear, yeah, RDT works exactly like some of you guys have suggested to make sure Helmsteed gets the help from Gondor, and it's 5 minutes. Now, the last version of RDT, the RDT 3.0. In version 3, we're going to make it very general. So there could be bit errors in the data packet, in the acknowledgement packets, but there could also be losses of the data packets or the acknowledgement packets. So the new assumption here is very general. The underlying channel might have bit errors, but it might also have packet losses, both at the data side as well as the ACK side. Now, all these mechanisms we have in version 2, checksum, X, retransmission, and the sequence numbers to avoid duplicates will help, but only help for, bit errors. So, in case of packet losses, not enough. So we need to add extra mechanisms. And the extra mechanism is this: the sender waits for some amount of time for the ACK to come back. If the ACK does not come back within the time window, then retransmit the packet. Okay, so retransmit the data packet if no ACK comes back within that timeout interval. All right, so what we're doing here is to require setting of a countdown timer per data packet being sent. Okay, so when the data being sent, timer gets started. That timer is going to tick. If ACK comes in before the timer expires, cancel the timer. If there's no ACK coming in and the timer expires, retransmit the data packet. Right? So that's pretty much all to address the packet loss issue. Now, hey, some of you might be wondering, what should be the timeout interval there, right? Hey, internet delay could be changing quite a lot over time. So these data packets can be just delayed, or the ACK packets coming back can just be delayed. So in case they are slightly longer than the timer that we have set up, then we will be retransmitting data unnecessarily. Yes, okay. Some of the retransmissions might be unnecessarily a duplicate. Just like when ACK is corrupted, the retransmission from the data sender in 2.1 is also unnecessary. But it's okay. We already have the mechanism right there, which is the sequence number. That's going to address the duplicate issue. So no worry, even though if we didn't set the timer quite right. It's just that there'll be a lot more unnecessary retransmission if the countdown timer is too short. All right, so hey, determining what is the duration for the countdown timer, that is also an art. We'll also see later in TCP how that is calculated, how that is estimated. All right, so yeah, sequence number is necessary again in RDT 3.0. The receiver needs to specify the sequence numbers for the ACKs, just like the data side needs to specify the sequence numbers for the data packets. And this is RDT 3.0 sender. Well, the usual technique, let me draw a line. So we just focus on one side of it, you'll see that the other side is similar. So what do we have here? Starting from the initial state, get a call from above, generate the packet, starting from sequence number 0, and what? Wow, we have these timer stuff, right? Starting a timer. And this is the transition next. If everything is going smoothly, receiving an ACK, it's not corrupted, and it's indeed ACK for 0. Then what? Stop timer. Now, if things don't go all that well, and the timer expires, then retransmit the packet and start the timer again. Because, hey, we just sent the data again, then the timer needs to be refreshed. Now, what is a bit unusual is in this transition. So what is this transition in 2.2? Well, the packet coming back from the receiver, if it's corrupted, or if it's clear that it's a negative acknowledgement, previously what did we do? We retransmit packet, right? Like calling UDT send packet here. But we actually do what? Nothing this time. Would that work? If it's corrupted ACK or a negative acknowledgement, and we do nothing, would that work? You know what? Hey, there's this transition, right? So sender here would just not work in case we get this explicit, okay, signals from the receiver, something is wrong. But eventually the timer is going to fire as well. So that packet is going to be retransmitted. It's just that, hey, with these situations, we're just, going to wait. So we'll just always wait until timer. How do you like that? Okay, so those who don't like that we don't retransmit quickly, say no, I don't. Those who don't mind, just say fine with me. Okay, okay, type it up on the chat. Let me know how you like that. All right. And next, we're gonna work through 4 scenarios. Okay, August is fine with that. We're gonna walk through 4 scenarios. Yeah, because it will work. We just wait longer, right? So we're gonna walk through 4 scenarios. The first 3 straightforward. Okay, so this video, 2 minutes, we'll just quickly go through the first 3 scenarios. Now I'll let you ponder how you like RDT 3.0. In the meantime, let's move on and see a few examples of RDT 3.0 in action. So scenario number 1 here is the null loss scenario. So everything is going well. Data, ag. So you see, packet 0 being sent, receiver here receive 0 and send back ag 0. Ag arriving at the sender side, yeah, receive what? Move to the wait for call from above for packet 1 state. So send packet 1, ag 1, send packet 0, ag 0, and go on and on and on. So this is a very straightforward scenario. Now the second scenario where we begin to see packet loss. Packet 0 go, ag 0 comes back. Packet 1 goes, but yeah, dropped. So what's going to happen here? The receiver is not going to receive anything. And the sender side has a timer, right? So that's going to tick, tick, tick until, yep, timeout. Resend packet 1 and restart timer. So ag 1 comes in. Hey, there's a timer going on here, but because ag comes in before the timer fires, so that timer gets canceled. So packet 0 go, ag 0 comes back. So this is the single packet loss scenario. And the third scenario is the ag loss case. So packet 0 gets out, ag 0 comes back. Packet 1 goes, and ag 1 get lost. What's going to happen there is the timer for packet 1 is going to tick and tick and tick until what? Expiration. So this is going to trigger packet 1 being resent, and finally ag 1 gets received, and data 0 being out again. Now what's a bit unusual here in scenario 3 versus 2 is that, yep, packet 1 was actually received already, but it's received again because the ag was the one being lost. Okay. No worry, because this is packet 1 and this is packet 1. For 2 consecutive packets carrying the same sequence number, receiver will not extract data and pass it further on. Receiver just send the ag back again, okay? And that's going to clear packet 1, and therefore packet 0 can go on further. All right, now the last scenario. This one is a little bit complicated. It will take 4 minutes to go over, but in the end, you will see that whether waiting or sending immediately, it's just a trade-off between time and traffic consumption. Scenario number 4 is to illustrate this case, premature timeout. So that is when the timeout interval is this long, but the ag and data takes a long time to take a round trip back. All right. The scenario goes like this. Packet 0 goes, ag 0 back. Packet 1 goes, ag 1, yeah, takes longer than usual to come back. So at this time point, timer expires and packet 1 here gets retransmitted. So packet 1 gets retransmitted before ag 1 can come back here. Right. So when packet 1 gets retransmitted, timer for packet 1 is restarted. But the good thing is, hey, ag 1 actually just, arrived. So from the sender's point of view, what's going to happen there is sender thought, ooh, ag for the packet I just sent has arrived, so cool. Cancel the timer and send the next packet. So packet 0 goes. And that's going to trigger ag 0 and come back. And data 1 goes, ag 1 comes back, data 0 goes, ACK 0 comes back. All right. Well, I hope it's just that easy, because we are actually not yet talking about when packet 1 arrives at the receiver, what's going to happen? Well, receiving packet 1 and receiver there will see this is a duplicate because I just received packet 1, right? So this is duplicate, ignore it, don't pass it up to the application layer, but still generate the acknowledgement to ensure that the sender is notified. So ACK1 will travel back. Now, sender here received ACK1. That's right after packet 0 is sent. What does that mean? Well, the sender there receiving a corrupted ACK or an acknowledgement that's not quite in sequence number that's expected, then it's probably a negative acknowledgement. So corrupted acknowledgement, negative acknowledgement, that should trigger retransmission in version 2. But in RDT 3.0, what do we do there? We actually ignore it, right? So some of us are not very comfortable about just simply wait until the timer. But you see here, hey, this will actually not trigger any further packet being generated. Okay. You'll see an advantage in the next scenario, where if we run RDT 3.0 with quick retransmission when there's ACK corruption or negative acknowledgement. So you see here, delay ACK, timeout expires first, packet 1 goes first. And ACK1 there generates packet 0 to go, and so on and so forth. Okay. So this generates ACK1 to send. But if, we are not running RDT 3.0, but an RDT 3.0 with what? Retransmission upon corrupted ACK or a negative ACK, then we send what? Packet 0. Okay, again. Because obviously packet 0 is corrupted, therefore we get ACK1. So retransmit packet 0. And that's going to trigger another ACK 0. You see, packet 1, packet 1. ACK1, ACK1. Packet 0, packet 0. ACK 0, ACK 0. So for every data packet, for every ACK packet, there's going to be what? A parallel sending, duplicate of it. Is that good? Even though we try to retransmit early. Not that good either, right? Comparing this case and the previous case. So a trade-off in the design of RDT 3.0 there. Okay, we thought that, hey, delay everything till the timer expire is not that smart. But we ended up saving bandwidth in the end, even though the retransmission is a little bit late. Yeah, so you see the trade-off. We can retransmit faster, but we ended up having 2 packets, 2 ACKs, 2 packets, 2 ACKs consistently the rest of the connection. Okay, so trade-off between bandwidth consumption and time. And there was a question from Zhenyu. In case D, the fourth scenario, if the second ACK1 reaches the receiver later than the second, is it going to break? That's a good question. I have to think it through, Zhenyu. Okay, I'll get back to you. Right? And with that said, we're supposed to go on with quiz 20, but we won't have time to complete quiz 20. So what I would suggest is that we'll then run quiz 20 the first thing tomorrow morning. Okay, so you guys need to make sure that one of your teammates will arrive on time for tomorrow morning and to answer quiz 20. And it is a fast solver gets bonus quiz. All right. And with that said, time is 2:09. It's time to say goodbye. I'll see you tomorrow morning. Okay, bye. Okay, bye.